Right now, as you're watching this video, there are roughly 200 billion trillion stars across the observable universe. Each one burns in the dark, and many host planets. With numbers like that, the universe should be busy. You'd expect alien megacities glowing on distant worlds. You'd expect our telescopes to overflow with radio traffic from thousands of species. The night sky should look alive with technology. So, where is everybody? Tonight we're exploring one of the most unsettling ideas in science: the Great Filter. It's a simple, sharp possibility. Somewhere between lifeless matter and galaxy-spanning civilizations, there are steps that almost no world manages to pass. If most planets fail at one of these steps early or late, the cosmos can be full of stars and still quiet. Before we dive in, tell us where you're listening from and what big space question keeps you up at night. And if stories like this grab you, a quick like and a subscribe help us keep making them. We keep the tone calm and clear so you can relax, but we won't drift into sleep story mode. This is a straight walk through a big idea at a pace that lets you think. First, the puzzle. If the galaxy has hundreds of billions of stars, and many have Earth-sized planets in the right temperature zone, intelligent life shouldn't be rare. Given time, at least some civilizations should build powerful tools. Radio, lasers, spacecraft. Those tools should leave traces we can detect. A narrow radio signal, a burst of light, a strange chemical mix in an atmosphere, even city lights on a planet's night side. Yet across decades of listening, we have no confirmed signal. That mismatch, lots of opportunity, almost no evidence, is often called the Fermi Paradox. It's not a strict law, it's common sense colliding with a quiet sky. The Great Filter is one way to resolve that collision. Picture a path with many gates. To go from raw chemistry to a spacefaring civilization, make it through each gate. Some are probably easy, others might be brutally hard. If even one gate is almost always closed, then almost no one makes it all the way. The universe can be packed with planets and still be quiet, because nearly every path ends early. Where might this filter sit? There are two main options. The filter could be behind us. That would mean Earth got lucky in rare, early ways. Maybe the origin of life is a freak event that almost never happens. Maybe complex cells, the kind with nuclei and mitochondria, are a once-in-a-trillion leap. Maybe multicellular life is fragile and usually stalls. Maybe intelligent, tool-using minds are far less likely than we assume. If the hardest steps are behind us, the silence makes sense. Most planets never even reach our level, so there are very few neighbors to hear. Or the filter could be ahead of us. That would mean the early steps, life, complexity, intelligence, happen fairly often. Civilizations bloom now and then, but when they gain powerful technology, they face a challenge they usually don't survive. That ahead filter could be self-inflicted, like a technology that runs out of control, or a conflict no one can stop. It could also be something natural we haven't met yet. In this view, the quiet sky is a warning. Many species reach our stage, and most don't get much further. Both stories fit what we know, because we don't know much. We've found thousands of exoplanets, which tells us planets are common. We've learned that life on Earth took billions of years to become complex, which hints that some steps might be slow or rare. We've also searched only a tiny fraction of the ways signals could appear. Different frequencies, different times, different parts of the sky. Our coverage so far is like sampling a cup of water from the ocean and concluding there are no fish. That small sample can't tell us whether the hardest step is past or future. It only suggests that at least one step is tough or the galaxy would likely be noisier. So, what do we do with this idea? We use it to think clearly. The Great Filter isn't doom. It's a framework. It pushes us to list the steps, check where the evidence points, and separate what we know from what we want to be true. It also helps with priorities. If the filter is behind us, patience and exploration make sense. Keep learning. Keep expanding. Don't rush. If it's ahead, then safety and wisdom matter even more. Build powerful tools carefully, audit them, and prevent risks we can foresee. In this episode, we'll map the puzzle in a practical way. We'll start with Fermi's question in plain language and a quick origin story. We'll define the Great Filter and what it actually claims. Then we'll look backward, from the first spark of life to complex cells, multicellular organisms, intelligence, and technology, asking which steps might be hard. After that, we'll look forward. What kinds of future risks could act as a filter? And what people mean by reducing existential risk without hype or panic. We'll also bring in data. How many planets have we confirmed? What fraction of the cosmic haystack have we really searched? What do the big listening projects actually report? Signals, false alarms, or just better upper limits? We'll revisit famous claims that didn't hold up and explain why no confirmed technosignatures doesn't equal no one's out there. Finally, we'll compare other explanations: rare earth, the zoo hypothesis, a dark forest, and see how they stack up. By the end, you'll have a clear picture of the possibilities and the limits. Not a horror story, not a lullaby, just a steady, honest account of what the silence might mean. If the hardest steps are in our past, that's rare good fortune. If the hardest step is in our future, we still have agency. We can make careful choices. We can value safety alongside discovery. We can aim for a long future, not just a fast one. So, a crowded universe, a quiet sky, and a theory that could place us on one side of a very tough gate or just before it. Let's lay out the facts, follow the logic, and see what the Great Filter might be telling us. Let's turn the big feeling into a clear question. If the Milky Way holds hundreds of billions of stars, and many of those stars have planets, why don't we see clear signs of advanced life? That's the heart of what people call the Fermi Paradox. It isn't a paradox in the math sense. It's a clash between expectation and observation. We expect many chances for intelligent life to appear, spread, and be noticed, but we don't see it. Who was Fermi, and why is his name on this? Enrico Fermi was a Nobel-winning physicist. In the summer of 1950, during a casual lunch at Los Alamos, he reportedly asked, "Where is everybody?" The group had been talking about UFO stories and cartoon jokes about stolen trash cans. Fermi's point wasn't about saucers. It was about scale and time. If a single civilization gained spaceflight and kept expanding, even slowly, it could cross the galaxy in a few million to tens of millions of years, much shorter than the age of the Milky Way. If that's even roughly true, then either such civilizations are rare, they don't expand, they don't last, or they're somehow hidden. Otherwise, we might see evidence everywhere: settlements, probes, or unmistakable signals. A few years later, this line of thinking blended with other ideas. In 1961, Frank Drake introduced the Drake equation, a back-of-the-envelope way to break the "are we alone" question into parts. Star formation rate, fraction with planets, fraction with life, with intelligence, with technology, and the average lifetime of detectable civilizations. The equation itself doesn't give an answer. It organizes our ignorance. Still, it sharpened the conversation. If you plug in optimistic numbers, even modest ones, you often get many expected civilizations in the galaxy. That brings us back to Fermi's question. If the math suggests many, why do we see 0 confirmed neighbors? It helps to define a few terms. A biosignature is a sign of biology, like a mix of gases in an atmosphere that's hard to make without life. A technosignature is a sign of technology, like a narrowband radio signal, a laser flash, an unusual light curve from a megastructure, city lights on a night side, or odd waste heat patterns. We've only started to search for either one in a serious, systematic way. Our tools are getting better, but they're still young. Now, what makes Fermi's question tricky is that we don't see anything can mean different things. We haven't looked enough. Space is enormous. Even if a clear, deliberate beacon is out there, it could be on a frequency we're not monitoring, aimed the wrong way, or transmitting on a schedule we've missed. Our searches cover a tiny slice of the cosmic haystack. Think of all the places, frequencies, time windows, and signal types that are possible. We've probed only a small fraction of that parameter space so far. They're rare or short-lived. Maybe intelligent technological life is incredibly uncommon, or it appears often but burns out quickly on cosmic timescales, centuries or millennia. So the odds of 2 civilizations overlapping in time and noticing each other are low. They don't signal. Even if civilizations survive, they may have no reason to broadcast. Early radio leakage like ours fades as technology improves. Fiber optics and tight beam links don't spill into space. Mature societies might be quiet by default. They're present but subtle. Signs could be ambiguous, buried in noise, or look like natural phenomena. Without a clear "this can't be natural" marker, we file them under interesting but not conclusive. They expand differently, or not at all. The picture of a civilization spreading with frontier towns across the stars may be wrong. Perhaps expansion is slow, local, or not a goal. Perhaps digital lives, virtual worlds, or tightly sustainable home systems are more attractive than galaxy-wide empires. Fermi's question doesn't tell us which of these is right. It just forces us to face the gap between "it seems like there should be many" and "we haven't confirmed any." There are one or more steps that almost always fail. Fermi's question is the symptom. The great filter is a possible cause. It says, yes, the galaxy could produce many beginnings, but there is at least one hurdle that very few, or maybe almost none, ever get past. That hurdle could be early life, starting at all, middle complex cells, multicellularity, intelligence, or late surviving the first dangerous century of high technology. The filter is not a single, precise theory. It's a framework that fits the silence and keeps us honest about what we don't know. 2 historical notes help here. First, the Hart-Tipler argument from Michael Hart in the 1970 seconds and Frank Tipler in the 1980 seconds. We'd expect to see clear evidence on Earth already, probes, visits, or other footprints. Since we don't, they concluded that intelligent extraterrestrials probably don't exist in the galaxy. Many researchers think that's too strong, because it assumes one style of expansion and ignores how little we've actually searched. Still, the Hart-Tipler line sharpened the stakes. Under certain assumptions, even a small number of expansionist civilizations would leave big marks. Second, search completeness matters. When you hear, "we looked and found nothing," the next question should be, how much did we really Look. If you stand on a beach, scoop 1 cup of water from the ocean, and find no fish, you can't conclude the ocean is empty. You need a survey plan. Which waters, which depths, which times, which nets. Modern SETI projects are building that plan. They set careful limits like no narrow-band transmitters stronger than X at Y distance in Z part of the sky, which turns silence from a vague feeling into actual data. Why spend time on these careful definitions? Because they shape how we interpret new results. Suppose we find a promising signal one day. We'll need to rule out Earth-based interference, satellites, and natural sources. If it's real and repeatable, it will change the whole debate. We could push the filter behind us. Life and intelligence are at least not unique, but might still argue about how common long-lived spacefaring cultures are. Or suppose we find strong biosignatures on many nearby exoplanets, but still no technosignatures. That would push the filter later. Life is common, technology rare, or short-lived. Each discovery or non-discovery moves the likely position of the filter. Finally, it's worth lowering the temperature of the conversation. The Fermi question is not an insult to human progress, nor is it evidence that doom is guaranteed. It's a way to test stories against facts. If the story says the galaxy should be loud, but the facts say it's quiet so far, then we need a better story. One that includes rarity, timing, behavior, or future risks. The Great Filter is one such story. It may be wrong, but it gives us clear claims we can compare with data as our surveys, telescopes, and instruments improve over the next decades. In short, Fermi's question sets the stage. It tells us there's a gap between what simple reasoning suggests and what we observe. The Great Filter is a candidate explanation for that gap. Next, we'll define the filter more precisely and lay out the steps where it might sit. Behind us in the deep past, or ahead of us in the near future. The Great Filter is not a wall in space. It's a simple idea about odds. Somewhere on the road from dead matter to a galaxy full of civilizations, there are one or more steps that are so unlikely that almost no world gets through them. Economist Robin Hanson popularized the term in 1998, using it to explain how a universe that seems friendly to life could still look empty of star-spanning cultures. 1. Think of it as a series of bottlenecks. You can pass many without trouble, but one narrow throat can determine the whole flow. Importantly, the Great Filter is agnostic about where the bottleneck occurs. It could be behind us in the deep past, meaning the hardest steps were the ones Earth already somehow managed to cross. Or it could be ahead of us in our future, meaning the dangerous part of the road is still coming. The idea doesn't tell us which. It only says at least one step is probably very hard. Otherwise, the galaxy would likely be buzzing with obvious evidence. How do we arrive at that conclusion? Start with the basic observation. Planets are common. We've confirmed thousands of exoplanets and inferred many more, including lots in the habitable zone, where liquid water could exist on a rocky surface. That suggests many shots on goal. Yet after decades of listening and looking for technosignatures, tight radio signals, laser flashes, odd waste heat, or unmistakable engineering, we have zero confirmed detections so far. Our search is still small compared to the full possibility space, but the silence pushes us to consider filters. Here's a clean way to picture it. Imagine the full journey from cosmic dust to starfarers as a chain of events. A stable star forms with a planetary system. A rocky world sits in a temperate zone with the right ingredients. Life appears, abiogenesis. Life persists and evolves complexity. Intelligent, technological species emerges. That species avoids self-destruction long enough to become durable. It expands or otherwise becomes conspicuous across interstellar distances. If the chance of each step is a probability less than 1, the final chance is the product of all those probabilities. Even if several links are easy, one truly tiny probability, say 1 in a billion, can dominate the whole chain. That's the heart of the great filter logic. A single very hard step can explain why a galaxy with many beginnings ends up with very few endings that look like "we're here" and obvious. Which steps might be hard? Researchers argue about several candidates. Abiogenesis, life from non-life. We do not yet know how life first began on Earth. There are promising pathways, RNA world ideas, hydrothermal vent chemistry, lipid vesicles, but no agreed-upon recipe. If abiogenesis requires a rare combination of conditions plus luck, that could be the filter. On the other hand, if life springs up quickly whenever conditions allow, this step might be easy. The leap to complex cells. Eukaryotes. For over a billion years, Earth hosted only simple cells. Complex cells with nuclei and mitochondria arrived later, possibly through symbiosis events that might be rare. If that merger is unusual, complexity itself could be a filter. Multicellularity and diverse body plans. Coordinating many cells into one organism with specialized tissues is non-trivial. It happened on Earth, but maybe that's uncommon elsewhere. Intelligence with technology. Many species are clever. Very few build radios, rockets, or computers. If combining big brains, language, culture, and long-term cooperation is statistically rare, this could be the bottleneck. Surviving the first dangerous century of high technology. Once a species can build powerful tools, nuclear weapons, engineered pathogens, autonomous systems, its risk profile changes. Avoiding catastrophic error or conflict long enough to become stable might be the hardest step. Becoming conspicuous. Even if a civilization survives, it might not broadcast or expand. If most choose to stay quiet or local, there may be little to detect from afar. Notice how the first 4 are behind us steps and the last 2 are ahead of us steps. The great filter doesn't pick a favorite. It gives us a menu and says, at least one of these probably has an extremely low pass rate. A related thread is the hard steps model from astrophysicist Brandon Carter and others. The idea is that if you have a limited window of time, say the billions of years before a planet becomes uninhabitable as its star brightens, then the timing of major evolutionary milestones on Earth, many of them happening relatively late, could hint that some steps are rare or slow by nature. If they were easy, you might expect them to happen earlier and more often. Not everyone agrees with this inference, and recent work revisits how strong it really is. But it's part of the debate. Late arrival can be a clue that at least one step was hard. So, is the great filter a single, sharp barrier or a stack of smaller difficulties? It could be either. Several mildly hard steps multiply into a very hard overall path. Imagine 5 steps with a 10% chance each. The product is 0.1. 5 equals 0.00001. Or 1 success in 100,000 tries. Add a couple more modest hurdles and your success rate plummets. Conversely, one truly rare event like abiogenesis at 1 in a trillion odds in a typical environment could dominate the rest. 2 common misunderstandings are worth clearing up. The great filter is not a doom prophecy. It doesn't say we're destined to fail. It says the path to galaxy-scale presence is probably rare. We might already be past the worst part. We don't know yet. The Great Filter doesn't require a conspiracy or hostile aliens. It's compatible with a quiet, natural universe in which most beginnings simply don't reach the flashy stage we could detect. Dark forest. Assumptions are necessary, though that's one separate hypothesis we'll cover later. What evidence would help place the filter? 3 kinds of discoveries would shift our bets. Life close to home, unrelated to us. If we found a second Genesis-independent life in our solar system, say on Mars, Europa, or Enceladus, it would suggest abiogenesis is not astronomically rare. That would push the filter forward toward later steps. As philosopher Nick Bostrom argued, this would be thrilling but also worrying. If early steps are easy, the silence is more likely caused by late, dangerous steps too. Biosignatures across many exoplanets. If telescopes consistently found atmospheres with chemical mixes best explained by life, that would also push the filter forward. Life is common, but technology or longevity is not a confirmed technosignature. A repeatable, clearly artificial signal or structure would push several filters behind us. Life and intelligence exist elsewhere, while still leaving open the question of how long such civilizations last and how many there are. There's also an anthropic angle. We can only observe from a world that has already passed whatever earlier filters exist. That selection effect can mislead us. For example, if abiogenesis is astronomically rare, we shouldn't be surprised to find ourselves on a planet where it did happen. Observers only arise on successful worlds. That doesn't make the step easy. It just biases our vantage point. Where does the Drake equation fit? You can see the Great Filter as a way of grouping the Drake terms into early stage and late stage factors. The product must be small enough to explain a quiet sky. Either the early factors, life, complexity, are tiny. The late factors, lifetime, expansion, conspicuity, are tiny. As data improve, we update which side looks more constraining. Finally, what does the Great Filter ask us to do? First, be honest about uncertainty. The hypothesis is a lens, not a verdict. Second, treat new evidence planet counts, biosignature surveys, technosignature searches with discipline. Non-detections can be information when they come with clear limits. No transmitters above X power in Y region. Third, plan for both cases. If the filter is behind us, we should value long horizons, exploration, and careful growth. If it's ahead, we should focus on reducing existential risks, building safe and interpretable technologies, and stabilizing global cooperation without wishful thinking or panic. In the next section, we'll test the behind us story against Earth's own record. Which steps in our past look like plausible filters? How rare might they be? And what can today's biology and geology actually tell us? If the Great Filter sits in the past, it means Earth already cleared the hardest gates. The universe can hold countless planets, yet very few make it as far as we have, because one or more early steps are brutally unlikely. That picture turns the quiet sky into good news. We may already be past the worst, but which steps look hard? And what does Earth's history actually show? Let's walk the timeline in plain language and mark the likely bottlenecks. 1. From rock and water to the first life, abiogenesis. Earth became habitable not long after it formed. The surface cooled, oceans appeared, and sometime more than 3.5 billion years ago, life shows up in the record first as chemical hints and ancient structures like stromatolites. The exact recipe for abiogenesis is still unknown. Ideas include an RNA world, where short genetic molecules copied themselves, chemistry at hydrothermal vents, or cycles in small pools that concentrated the right ingredients. We don't yet have a lab demonstration that runs from simple prebiotic chemicals all the way to a self-sustaining cell. Two stories can fit the same facts here. One says, life appeared relatively quickly after conditions stabilized, so maybe abiogenesis is easy whenever the environment is decent. The other says, we are looking at a single lucky world, and of course observers show up on a rare success. That doesn't mean the step is easy. With one data point, both stories survive. If we later find independent life in our own solar system on Mars, Europa, or Enceladus, that would push this step toward common. If we don't, the door stays open. That abiogenesis is the great filter. For now, unknown, not confirmed. 2. From simple cells to complex cells, eukaryotes. For more than 1 billion years, Earth was a planet of simple cells. Complex cells, the kind with nuclei and mitochondria, appear later. One leading idea says, mitochondria began as free bacteria that took up residence inside another cell, creating a partnership that let the host power a much larger genome and more complex machinery. If that event was weird and rare, then the path to complex bodies may be rare too. Some researchers argue this was a singular, unlikely merger that unlocked multicellular animals and plants. Others think multiple roots could exist, and we just haven't seen them elsewhere yet. Either way, the timing matters. There's a long delay between early life and widespread complexity. That delay could be a clue that becoming complex is a hard step, not a quick upgrade. 3. Oxygen and the energy problem. Oxygen is rocket fuel for cells. For most of Earth's history, the atmosphere had little free oxygen. Then came the great oxidation event, a rise linked to photosynthetic microbes, changing the chemistry of ocean and air. Later, oxygen levels rose again, paving the way for large, energy-hungry bodies. This might sound like a chemistry footnote, but it's a big deal. High-energy metabolisms allow active animals, big brains, and fast ecosystems. If oxygenation depends on a long, fragile chain of planetary processes, that could be another bottleneck. Not every planet will run that chain fast enough or at all before its star bakes it. Multicellularity and complex body plans. Life became multicellular many times in animals, plants, fungi, and various algae. That suggests multicellularity itself may not be ultra-rare, but complex multicellularity, coordinated tissues, circulatory systems, nervous systems took time and likely required previous upgrades. Energetic cells, oxygen-rich environments, and genetic toolkits that can pattern a body. Think the toolbox genes that switch other genes on and off. The famous Cambrian explosion around 541 million years ago wasn't a single blast but a long ramp where many animal groups diversified. Was that step hard? The independent origins argue maybe not. The long wait and prerequisites argue maybe yes. Reasonable people disagree. 5. Intelligence with cumulative culture and technology. Plenty of species are smart in their own ways. Crows using tools, octopuses solving puzzles, whales communicating across miles. But cumulative culture, where innovations stack over generations, is rare. Humans combined language, teaching, division of labor, and a hunger to tinker. That ratchet lets simple tools grow into complex technology. Is that leap common wherever brains evolve, or was it an unusual package deal that came together once on this world? We don't know. The fact that only one lineage on Earth built radio in 4+ billion years tempts the conclusion that this step is rare. The fact that intelligence has evolved many times tempts the opposite, again. The evidence allows both. 6. Planetary luck. Long stability, plate tectonics, magnetic field, and a big moon. The rare Earth perspective says Earth might be special for boring reasons that matter a lot. We have plate tectonics that recycle nutrients and help regulate climate over deep time. We have a magnetic field that shields our atmosphere from solar wind. We have a relatively stable climate and long stretches without planets sterilizing impacts. We also have a large moon that may help stabilize Earth's tilt, preventing wild swings in climate. None of these are guaranteed on a random rocky world. If you need several of them at once, the odds multiply downward. That doesn't mean Earth is unique. It means Earth-like might be a small subset of rocky and wet. 7. The clock. A limited window of habitability. Stars brighten over time. Many planets get a few billion years in the comfortable zone before their oceans evaporate or their atmospheres shift. On Earth, complex animals showed up late compared to the planet's total habitable window. That lateness is part of the hard steps argument from Brandon Carter and others. If easy steps tend to happen early, then seeing several major steps occur late hints they're inherently tough and time-consuming. Not everyone buys that argument as originally stated. Newer work re-examines the statistics and astrobiology and suggests we should be cautious about overreading one timeline. But the limited window picture is simple. Even if everything is possible, you still have to do it fast enough. Put those pieces together and you can sketch a credible behind-us great filter. Maybe abiogenesis is rare. Planets like Earth form, but only a tiny fraction spark life before conditions change. Maybe complex cells are rare. Even with life, most worlds never get the mitochondria-style energy leap needed to support big genomes and complex bodies. 3. Maybe the chemistry never resets the atmosphere. Without oxygenation, high-energy metabolisms and big-brained animals are constrained. 4. 5. Maybe the window closes. Stars brighten, climates swing. Time runs out. 7. Maybe cumulative culture is rare. Intelligence appears, but the ratchet that builds technology almost never does. Each maybe reduces the final odds. Together, they can make the path from chemistry to radio incredibly narrow, even if planets are common. There's also a soft form of the argument that doesn't require any single miracle. It says, even if none of the steps are astronomically rare by themselves, several mildly hard steps in sequence make the whole chain rare. 5 steps with a 10% pass rate yield 1 success in 100,000 tries. Add a couple more, and you're in 1 in millions territory. In that world, Earth is lucky, not because of a single magic coin flip, but because of a run of good flips. Now, some reasons to be careful with the behind-us story: selection bias, anthropic principle. Of course, we find ourselves on a world that made it through the early gates we couldn't observe, from a world that didn't. That doesn't mean the gates were extraordinarily hard. It means our vantage point is biased. The bias is real. Interpreting it takes care. Early life appears early. If abiogenesis happened quickly after Earth cooled, that hints it might be easy under the right conditions. That clue is contested, but it leans against abiogenesis is the filter. Multicellularity evolved many times, independent origins in plants, animals, fungi, and algae suggest coordination among cells isn't impossibly hard, given the basics. Brains keep getting bigger. Across mammals and birds, multiple lineages march toward higher cognition. That hints intelligence can be a convergent trend when environments push for it. Recent reassessments of hard steps timing, newer work, including a 2025 reassessment, argues the late timing of milestones on Earth does not, by itself, prove extreme difficulty. Planetary habitability may have come in fits and starts, and chance plays a bigger role than early models assumed. In short, the timeline is compatible with hard steps, but doesn't force them. In other words, the behind us filter is plausible, not proven. Several facts line up with it. Several keep us humble. What would move the needle? A few discoveries would shift confidence toward or away from a behind us filter. A second genesis nearby. Life on Mars or in an icy moon's ocean, clearly unrelated to Earth, would hurt the abiogenesis is rare story and push the filter later to common biosignatures on exoplanets. If next-generation telescopes spot strong, repeated signs of life in many atmospheres, early steps look easier, and later steps, technology or longevity, look harder. Evidence of complex life elsewhere, fossils on Mars, unlikely but decisive, or clear spectral signs of complex biospheres on exoplanets would push even more of the filter behind us. A confirmed technosignature, this would move multiple steps off the rare list at once. Life, complexity, intelligence, somewhere else, while still leaving open how many last. If the filter is behind us, practical meaning. If the hardest gates are in our past, it changes the mood but not the homework. Patience and stewardship. Our job is to avoid unforced errors while we learn and expand. The future may be long if we don't cut it short. Exploration matters. Finding even simple life elsewhere would rewrite the odds and our understanding of our own path. Robotic missions and powerful telescopes are not just cool, they're tests of the filter's location. No victory laps. Behind us doesn't mean no dangers ahead. It means we might be unusually lucky already. Lucky species can still make bad choices. A simple scoreboard so far, likely hard step candidates behind us: eukaryogenesis, energy leap, oxygenation and stable climate choreography, cumulative culture leading to advanced technology, possibly easier than they look, basic life, pending new evidence, multicellularity, given repeated origins, big unknowns that dominate the picture. How common habitable windows really are, whether long-term stability like Earth's is typical or rare, how often intelligence ratchets into technology. A final note on tone. The behind us great filter is the hopeful version. It says the silence is not a threat. It's a reminder that we live on a world that beat long odds long ago. That hope should make us careful, not careless. We may be early. We may be rare. If so, what we do with the next few centuries matters even more. Next up, we'll examine the other side of the ledger. The ahead of us filter. What if early steps are common, but civilizations often falter right after they gain powerful tools? What are the realistic, non-sci-fi ways that could happen, and what could we do about it? If the great filter sits ahead of us, the quiet sky is less a mystery and more a warning label. In this view, the early steps toward life and even intelligence aren't impossibly rare. Planets with oceans form, microbes take hold, ecosystems stabilize, thinking creatures appear. The trouble comes right after a young civilization discovers powerful tools. That stretch fast progress with thin safety is narrow. Many cultures burn out. Others stall. Only a few last long enough to spread, settle, or leave bright signatures that are easy to spot from light years away. That alone could explain why our instruments keep finding nothing conclusive. Not because no one else ever starts, but because very few keep going. 3 facts push us to take this seriously. First, planets are common. We've confirmed thousands and inferred many more, including rocky worlds in temperate zones. The number of shots on goal is huge. Second, our searches are still small. A small search can't prove a negative, but if the galaxy were packed with long-lived, chatty cultures, we might expect at least a handful of unmistakable hits by now. We don't have them. Third, modern tools are double-edged. For the first time in Earth's history, one species can alter planet-scale systems. Energy, climate, food, information for better or worse in a single lifetime. Power has arrived faster than wisdom. That gap may be what the filter is made of. Carl Sagan once called it our technological adolescence. The period when a species gains tools that can end its own story faster than it can mature its judgment. Nuclear weapons were the first clear example. Biotech and advanced AI may be next. Add brittle infrastructure, climate pressure, and geopolitical mistrust, and you get a cluster of hazards that interact. The great filter, in this framing, isn't one monster. It's a bundle. Survive the bundle, and odds improve. Fail, and you vanish. The pattern is simple. As a civilization connects more parts, power grids, satellites, shipping lanes, markets, it gains reach and speed. It also becomes vulnerable to cascades. A small spark in a tightly coupled system can ripple into a wide failure. Add tools whose capabilities rise each year, and you have conditions for large mistakes that appear without much warning. Artificial intelligence is a capability multiplier. It can accelerate science, improve healthcare, and manage complex systems. It can also lower the barrier to launching sophisticated attacks, produce persuasive fakes at scale, and optimize for goals we didn't mean to set. There are 2 broad risk shapes here. Loss of control. Highly capable systems may pursue objectives in ways that diverge from human intent, especially if goals are underspecified or conflict with human values. If such systems are embedded deep in critical infrastructure grids, logistics, finance, emergency response, unintended behavior can cascade before humans grasp what's happening. The worry isn't a movie villain. It's a fast, opaque optimization process, pushing hard in the wrong direction, while humans lack clear levers to intervene. Today's models already challenge our ability to audit and predict. As capability rises, the window to understand and steer can shrink. Even well-behaved tools can be used badly. Authoritarians, criminal groups, or simply careless organizations can pair powerful models with other technologies to amplify harm. Targeted cyber intrusions, automated scams, destabilizing propaganda, or rapid design help for dangerous agents. In a race for advantage, incentives reward shipping first and fixing later. That habit works for social apps. It's a terrible fit for systems that touch safety-critical domains. None of this makes catastrophe inevitable. It does mean safety and governance must scale with capability. Independent evaluations before deployment, red team testing by outsiders, auditing large training runs, reliable containment and shutdown methods, and clear responsibility for harm. If most young civilizations skipped that homework, many could stumble right here. Bio-risk, dual use, cheaper tools, thin margins. Biology has the same double edge. Tools that let us read and write genetic information are transforming medicine and agriculture. They also carry dual-use potential. Methods that cure can be misused to harm. As software improves and costs fall, more people can do more biology in more places. That's good for discovery and hard for security. The core risk isn't in exotic recipes. It's in structure. A world with many actors able to modify organisms is a world where accidents happen more often and where a few malicious choices can do unusual damage. We already live with thin margins. Hospitals near capacity, supply chains tuned for speed, public trust stretched. An event with higher severity or faster spread than we're used to can stress systems faster than they adapt. If most civilizations reach the cheap biotech, weak safeguards, low trust phase before they build strong biosecurity norms and rapid response capacity, many will fail this test. Geopolitics. Sharp tools, short timelines. Great power politics never left. In a high-tech century, stakes rise. A large conventional war could escalate by mistake through false alarms, misread signals, or panic into nuclear use. Even a limited exchange would be a global catastrophe. A larger one could trigger climate and agricultural effects that last for years. Meanwhile, attacks on satellites, energy systems, or financial networks could produce wide cascading failures without a single mushroom cloud. Two trends make this worse. Decision windows are shrinking as sensors and algorithms accelerate detection and response. Minutes replace hours, and domains are entangled. A cyber incident bleeds into space systems, which bleeds into conventional forces. When leaders have little time to decide and many systems are opaque, accidents get easier. If that pattern is common across young civilizations, a lot of timelines will end early. Climate and environment. Pressure multipliers. Climate change isn't a single switch. It's a stack of stresses: heat, drought, fires, stronger storms, shifting disease ranges, crop failures, sea level rise. These stresses magnify other risks. Under pressure, people move, politics hardens, and mistakes compound. At the same time, proposals to cool the planet directly, various geoengineering ideas carry risks if done hastily or by one country acting alone. None of this guarantees collapse, but as a multiplier, climate stress makes war more likely, bio-risk harder to manage, and infrastructure failures more costly. The filter here isn't only physics. It's the politics of a warming world, making good choices rarer. Complex systems, tight coupling, little slack. Modern life runs on networks: power, data, food, shipping, finance, satellites. These networks are efficient because they are tightly coupled. The downside: tightly coupled systems fail fast. A single wrong assumption can ripple through many layers. Think of blackouts, financial crises, or global supply shocks. Now scale up. Add sharper tools and shorten timelines. A society that optimizes for speed and cost at every node, with little redundancy, becomes fragile. In a fragile system, medium shocks produce large effects. If most young civilizations build shiny, brittle systems before they build robust ones, that looks like a filter, quiet by design. Survival without a beacon. There's a softer filter that doesn't kill anyone. It hides them from our view. As cultures mature, they may become quiet by design. Radio leakage fades as fiber optics and tight beam links take over. Encryption becomes standard, hiding traffic in plain sight. Activity shifts into virtual environments with modest physical footprints. Energy is used efficiently, leaving little waste heat. A long-lived civilization built like this can be healthy and stable, yet hard to spot from light years away. That could mean that the galaxy is full of neighbors who are simply difficult to notice. But even this quiet picture doesn't dodge adolescence. You still have to survive the loud, wasteful phase to reach the quiet one. In the Drake equation, the last term is L, the average lifetime of detectable civilizations. If L is small, hundreds or a few thousands of years, the odds of overlap are low. You can have many starts and still almost never have two who can hear each other at the same time. The ahead of us view claims L tends to be small because adolescence is hard to outgrow. The mission for any species that wants a long future is to raise L to build systems, habits, and norms that lengthen the lifetime of a technological society. Consider two future datasets. Dataset A. Telescopes find strong biosignatures, chemical mixes that strongly suggest life on many planets. But technosignatures stay absent. That pushes the filter forward. Life is common. Technology or longevity is rare. It's thrilling news for biology and sobering news for the future. Dataset B. We detect a clear, repeatable technosignature, a narrowband radio signal with the right traits, a deliberate laser ping, or something stranger that can't be natural, that instantly moves several early steps behind us. Life and intelligence exist elsewhere. But if such signals remain rare even after one detection, it still hints that L is low. Some make it, most don't last. Either dataset would sharpen the map, neither ends the debate. We would still have to answer, what makes a civilization last? A filter doesn't need a supervillain. It can be made of regular mistakes repeated at high speed with larger tools. Incentives favor speed. Markets and politics reward shipping, not safety until after failure. Externalities pile up. Costs are pushed onto the future or onto distant communities. The bill arrives all at once. Information is polluted. If truth-seeking fails, planning fails. Complex risks need shared facts. Coordination lags. The people able to reduce risk don't bear the full cost of failure, so they underinvest in prevention. We know these patterns. We live with them now. The ahead of us filter says those same patterns, with more power behind them, can end futures. If the filter is ahead, the task is clear. Extend the lifetime of a technological civilization without freezing progress. That's a toolbox, not a slogan. AI, safety, and governance. Evaluate powerful models before wide release. Let independent teams red team them. Track and audit very large training runs so we know who is creating what capability. Build reliable containment and shutdown methods for high-risk systems. Clarify legal responsibility for harm. Create incident hotlines and coordination channels so weird events don't cause panic or miscalculation. Biosecurity. Make strong lab safety a real norm with audits that matter. Improve ventilation and waste handling, especially where risky work happens. Build routine, privacy-preserving pathogen surveillance to catch unusual patterns early. Keep rapid vaccine and therapy platforms warm between crises. Put strict controls and clear incentives around the riskiest research while keeping routes open for safe, beneficial work. Nuclear risk reduction. Maintain early warning systems to reduce false alarms. Keep lines of communication open even between rivals. Reduce hair trigger postures where possible. Practice joint crisis simulations so leaders and militaries have muscle memory for de-escalation under pressure. Resilience by design. Add buffers to power grids and supply chains. Stock critical inputs. Segment networks to limit the blast radius of failures. Plan for space weather. Run blackout drills. Build manual fallbacks for digital systems that control physical machines. Efficiency is not the only metric. Slack is survival. Planetary defense. Keep scanning for near-Earth objects. Mature deflection methods. Rehearse decision paths so a real threat doesn't meet a cold start. Truth infrastructure. Support institutions that can investigate accidents and near misses without political punishment. Protect rigorous science and responsible journalism. During crises, give experts and the public spaces to see the same vetted facts. Focused cooperation. No world government required. We do need a few narrow, strong agreements in high-risk areas, backed by verification that builds trust slowly. The goal is to make races to the bottom less profitable and cooperation slightly easier. None of these moves guarantee success. Together, they raise L. They turn a fragile, short-lived timeline into one that persists long enough to learn. It's easy to list dangers. It's just as important to list capacities. Safety scales, too. Vaccines, public health, monitoring tools, and verification tech are products of science. If we choose to fund and deploy them, they can grow as fast as the risks. We've passed hard tests. The world navigated decades of nuclear tension without a world-ending exchange. Disaster response networks, while imperfect, are far better than a century ago. Technology is mostly dual use. The same AI that could speed harm also speeds countermeasures. The same gene tools that could be misused also enable rapid cures. Governance choices matter more than the tool by itself. Cultures can learn. Aviation got safer because we investigated crashes without blame and shared lessons. Medicine improved through trials and reporting. Software improved through code review and reproducible builds. Those are templates for the high-stakes areas now on the table. Optimism here isn't a feeling. It's a plan. We decide which capacities to scale. If the ahead-of-us filter is real and a few civilizations pass it, what distinguishes them? Probably not perfect leaders or miracle foresight. More likely, boring strengths, redundancy, accountability, transparency, error-correcting institutions, and a habit of pausing to test when stakes are high. Survivors pay for slack up front, so systems hold under stress. From the outside, they may look dull. Steady lights, little leakage, few fireworks. Inside, they're rich and complex. They aimed cleverness at stability first, spectacle second. After a long stretch, such cultures might choose to be visible again on purpose, with a deliberate beacon or a careful probe. If so, today's quiet sky doubles as a message. Practice the habits that make you one of the survivors. The ahead of us great filter says this century matters more than most. The exact risks will evolve, but the pattern holds. Capability races ahead. Wisdom must be built. If we raise L, extend the lifetime of a technological civilization, everything else gets easier. We'll have time to search well, to explore gently, and eventually to speak in a way someone else might hear. We don't need perfection. We need margin. Enough caution to avoid self-made disasters, enough coordination to handle shared risks, and enough curiosity to keep our eyes up while we do it. That mix sounds modest, but the payoff is huge. A future where our descendants choose what kind of civilization to be. And maybe, one day, What kind of neighbor? If the great filter is about odds, we should pin down the numbers we actually have. How many planets are confirmed? How many could be friendly to life? And how much of that big number is hype versus hard data? As of October 2025, NASA's Exoplanet Archive lists a little over 6,000 confirmed exoplanets. We crossed the 6,000 milestone in September 2025, and the curve is still rising, with dozens added each month as new discoveries clear peer review and get logged. That headline matters for one reason. It shows that planets are the rule, not the exception. Solar systems like ours aren't rare museum pieces. They're normal outcomes of star formation. How we find these planets shapes what we see. Transits: a planet crosses its star and dims it slightly, deliver the majority of known worlds. Watching repeated dips lets us measure size and orbital period. Radial velocity: a star wobbles from a planet's tug, delivers most of the rest and tells us the planet's minimum mass. Microlensing: gravity acting as a lens during a precise alignment, catches planets farther from their stars, but each event is one time and hard to repeat. Direct imaging, taking an actual picture of a planet, is still rare and favors giant, young, far-out worlds glowing with leftover heat. Each method is powerful. Each is biased. Transits and radial velocity naturally prefer big planets on short orbits because they make deeper dips and stronger wobbles more often. Microlensing sees colder, wider orbits, but only when the sky lines up just so. Direct imaging struggles near bright starlight and therefore misses small, cool, Earth-like worlds. The result: our 6,000-plus catalog is real, but it's also the easy-to-find slice of what's actually out there. 4. We can't directly count true Earth twins yet, so astronomers use Kepler's statistics to estimate how common small, rocky planets in just right orbits are. The answer depends on where you draw the lines, how wide the temperate zone is, what size range counts as Earth-like, and how complete the data are near one-year orbits. With those caveats, published studies land anywhere from a few percent to several tens of percent of Sun-like stars hosting at least one small planet in a temperate orbit. In plain terms, rocky, potentially mild temperature worlds aren't rare, and the Milky Way could hold billions of them. The uncertainty is large, but the main point holds. 2 cautions matter. First, being in the habitable zone does not mean the planet is actually habitable. Venus falls inside some textbook definitions, yet is a 900 degrees Fahrenheit pressure cooker. Second, roughly Earth-sized says nothing about atmospheres, magnetic fields, plate tectonics, oceans, or chemistry, all of which drive long-term habitability. Eta Earth is a first-pass statistic, not a promise of blue skies and shallow seas. Kepler stared at one patch of sky for years, trading breadth for depth. TESS flipped that approach, scanning almost the entire sky to find planets around bright, nearby stars. Those are perfect targets for follow-up. Once TESS flags a world, other telescopes can measure its mass, look for additional planets, and most exciting, probe the atmosphere when the planet transits. TESS has already produced hundreds of confirmed planets and thousands of candidates, many around stars close enough for detailed study. The James Webb Space Telescope, JWST, is now doing what Kepler couldn't: reading the chemical fingerprints in some exoplanet atmospheres by watching how starlight filters through them during transits. In 2023, JWST reported methane and carbon dioxide in the atmosphere of K2-18b, a sub-Neptune in its star's temperate zone, sparking debate about exotic Haitian oceans. In 2025, headlines suggested hints of dimethyl sulfide, Na, a gas linked to biology on Earth. But follow-up teams and NASA-linked summaries urged caution. No conclusive DMS detection and no confirmed sign of life. The lesson is the same one we've learned on Mars. Extraordinary claims need multiple, independent lines of evidence, repeated over time. 2 upcoming space missions will sharpen the senses and prepare for the next leap. ESA's Plato will monitor hundreds of thousands of mostly sun-like stars to find small planets on year-long orbits, exactly the sweet spot we need to firm up Eta Earth. It will also help estimate stellar ages, which matters for understanding how long planets have had to develop life. NASA's Nancy Grace Roman Space Telescope will run a massive microlensing survey to catch planets on wider orbits, the ones our current methods undercount, and will demonstrate a high-contrast coronagraph. That tech is a pathfinder toward directly imaging Earth-like planets around nearby stars in the 2030 seconds. 2040 seconds. Add in ground-based heavyweights like upgraded radial velocity spectrographs, and the picture is clear. This decade will trim the error bars on Eta Earth, fill the catalog beyond hot, short-period worlds, and get us ready to see small, temperate planets instead of just inferring them. Why lots of planets doesn't answer Fermi's question. Hearing billions of temperate rocky planets makes it tempting to say, case closed, there must be many civilizations. But quantity doesn't erase the core Fermi puzzle. 3 reasons. Search bias. Our catalog leans toward easy planets, big, close in. Earth analogs are the hardest to find, so they're underrepresented for now. Search size. Even after decades of listening, our techno-signature search is a tiny sample of the possibilities. Different frequencies, sky locations, polarizations, time windows, message types. The cosmic haystack has many dimensions, and we've checked only a thin slice. One careful estimate compared our past radio search volume to a hot tub's worth of water drawn from all Earth's oceans. Not finding a fish in that cup doesn't prove the ocean is empty. It proves your sample is small. Lifetime and behavior. Even if life is common, long-lived, detectable civilizations might be rare. If most are short-lived or choose quiet, efficient communications, tight beams, encryption, fiber optics that don't leak, the galaxy can host many minds and still look silent to us. In short, the big planet counts keep the paradox alive. They make the "why so quiet?" question sharper, not weaker. Myths to retire. We've directly photographed loads of exoplanets. Earth twins are next. We've directly imaged fewer than 100, mostly giant planets, far from their stars. Imaging an Earth next to a sun requires blocking starlight by factors of billions. Roman's coronagraph will demo key tricks, and the proposed Habitable Worlds Observatory aims to go the last mile, but we're not there yet. One molecule equals life. No, many molecules linked to life on Earth also have abiotic sources. Robust life detection needs context, planet, type, temperature, multiple biosignature gases that fit together, and repeatable measurements. That's why the K2-18b buzz was exciting and debunk-prone at the same time. 6,000 planets means we basically know the galaxy's inventory. 6,000 is huge compared to the 1,990 seconds. It's microscopic compared to reality. We're seeing the bright end first, the long tail cooler, smaller, more distant worlds requires the next wave of instruments. What we can say with confidence, planets are everywhere. Star formation naturally makes planetary systems. Our confirmed list passed 6,000 and climbs steadily. Discovery methods shape the sample. Transits and radial velocity dominate today's catalog and favor short-period planets. Microlensing and imaging cover farther and larger regimes. Each method is a keyhole, not a window wall. Earth-like is plausible but not yet counted. Eta Earth is likely not tiny, but the range is still broad. Kepler gave the first strong hints. Plato and Roman will narrow the estimate and reduce our reliance on extrapolation. Atmospheres are the next gate. JWST has opened atmospheric chemistry for a handful of worlds. Future telescopes will scale that up and, eventually, directly image small planets around nearby stars to check for biosignature combinations, not one-off molecules. Today's silence is not a verdict. The haystack is enormous, our sample is small, and long-lived. Quiet civilizations may be both rare and hard to notice. No confirmed technosignatures yet is a data point, not a final answer. The planet census slices both ways. On one hand, a large potential inventory of temperate, rocky worlds keeps the pressure on. If there are so many shots on goal, why is the sky so quiet? On the other, our method biases. Tiny search fraction, and the lifetime. Behavior issues mean a quiet result in 2025 is compatible with many big-picture stories. A behind-us filter, rare abiogenesis, rare complex cells, or other hard steps. So there just aren't many peers to hear, and ahead of us, filter civilizations often fail during technological adolescence. So, detectable lifetimes are short. A quiet-by-design, galaxy-mature civilizations use tight beams, encryption, and efficient energy, so there's little leakage to catch unless we're in the path. Which story is true will be shaped by the next decade of data. If Plato and Roman show that Earth-size, temperate planets are common, and JWST or its successors begin to see biosignature-like atmospheres on multiple worlds, then early steps look easier and the likely filter moves forward. If, instead, Earth-like planets prove rare, and biosignatures stay elusive even with better instruments, then the bottleneck may sit behind us. And if we catch a clear, repeatable technosignature, we instantly move several filters behind us. Life and intelligence are not unique, while keeping the question of lifetime wide open. Either way, counting worlds is not just trivia. It's the denominator in the biggest fraction we've ever tried to estimate. Have we looked hard enough? Short answer. Longer answer. It depends on what you mean by looked. If looked means we've pointed world-class instruments at thousands of stars and swept billions of radio channels and some optical bands, then yes, we're looking. If looked means we've sampled a meaningful fraction of all the places, times, frequencies, and signal types another civilization might use, the honest answer is no. Our search so far is a thimble dipped into a very large ocean. Let's make that concrete and keep the math light. Finding a technosignature is not like spotting a lighthouse in the dark. It's like searching a warehouse full of hay bales for a handful of needles when you're not even sure what shape the needles are. The haystack has many dimensions. Frequency. Radio signals can live almost anywhere on a huge dial. Classic searches hang out in relatively quiet windows, but even there you're slicing billions of tiny channels. You never scan them all at once. Sky position, Do you stare at a short list of nearby stars? Sweep the whole sky? Park on the galactic plane? Each choice trades depth for breadth. Most programs mix targeted lists with wider, shallower passes. Time. A transmitter could be always on, or it could wink for seconds once an hour, once a day, or once a year. Many observations last minutes per target. That means you might simply miss the blink, signal style. The easiest thing to recognize is a narrow band tone, a razor-thin spike that nature rarely makes. But advanced builders could use spread spectrum, frequency hopping, short laser flashes, or formats that look like noise, unless you know the key. Motion and drift. Relative motion shifts frequencies. Pipelines correct for a range of Doppler drifts, but not every possible rate. Sensitivity. A weak transmitter nearby can be easier to spot than a strong one far away. Instruments set upper limits, not absolute statements. If a signal stronger than X were present here and then, we would have seen it. Multiply those dimensions and you get a possibility space so large that even big surveys barely dust the shelves. Radio SETI. This is the backbone. Large dishes and arrays scan millions to billions of channels around targeted stars and survey regions. Modern pipelines remove obvious human interference, correct for Doppler drift, and flag anything that looks narrow, persistent, or drifting just so. A typical run produces thousands of candidates. Nearly all turn out to be Earth-made. Satellites, aircraft, ground transmitters, weird reflections, or quirks of the electronics. The success here isn't a hello yet. It's discipline. Teams rapidly triage candidates and publish upper limits, clear statements about what was checked and what would have been seen. That turns silence into data. Optical and near-infrared SETI. Instead of radio, some groups hunt for nanosecond-scale laser flashes or extremely narrow optical lines nature rarely makes. A modest facility could send these. A modest facility can detect them. We've logged hundreds of thousands of star hours. So far, no confirmed artificial flashes. Again, that's a constraint, not a dead end. Commensal. Many observatories now collect technosignature data while doing regular astronomy. It's efficient and generates massive archives. But you inherit whatever pointing and frequencies the primary program chose. Still, every hour adds to the pile. Megastructures and other byproducts. Not all technosignatures are beacons. Some would be side effects. Unusual mid-infrared heat from heavy energy use, odd light curve dips that could hint at orbiting structures, unnatural chemistry in a planet's air, or even artifacts parked in stable niches in our solar system. These searches have taught us mostly what isn't out there nearby. Galaxy-spanning energy empires look rare. Dramatic alien dimmers have natural explanations, and local space seems empty of obvious relics at the scales we've checked. Open data and reanalysis. A healthy trend. Sharing raw and processed data. Independent teams can build new filters, try different drift ranges, or run anomaly detectors. Several interesting hits in the past were confirmed as human interference or ruled out by fresh rechecks on shared files. A quick sense check. Suppose you want to cover just 1 to 10 gigahertz, a classic window. That's 9 billion 1 Hz channels. Your receiver can process a lot of spectrum at once, but not all of it. Now add time. You stare at a star for 10 minutes. If the transmitter blinks once an hour, you had a 1 in 6 chance. If it blinks daily, 1 in 144. Monthly? Forget it. Add sky. There are millions of promising stars. Add signal styles, tones, bursts, sweeps, hops. The fraction of the haystack touched by any one observation gets tiny, fast. This isn't a reason to quit. It's a reason to scale up and to design smarter campaigns. Why the quiet doesn't settle the question. People hear no signals and jump to extremes. Either we're alone or they're hiding. The more useful framing is, a non-detection at known sensitivity shrinks the space of possibilities. It says that in those bands, at those times, aimed there, nothing above a certain power level was present. Do that across more bands, more stars, longer times, and the constraints start to bite. You can eventually rule out a galaxy full of loud, always-on beacons. You do not rule out rare beacons, cautious neighbors, short-lived broadcast phases, or formats we aren't tuned to recognize. The interference problem, radio frequency interference (RFI), is the messy reality. Aircraft, satellites, ground stations, electric fences, microwave links, even the observatory's own electronics throw off signals. Some bounce off the atmosphere and appear to come from the sky. Others mimic the narrowband drift we seek. Good pipelines fight back with shape tests, true, narrow lines versus messy splatter. Drift tests. Does the frequency shift match sky motion or a known satellite track? Multi-beam checks. Real sky signals appear in the on-target beam, not all beams. On-off pointing. Look at target, then away, then back. Earth-made signals often follow the telescope. Sky signals follow the sky. Even with all this, promising candidates sometimes survive to follow up, then vanish or reveal a human origin. That's normal. It's also why rapid coordinated re-observations from multiple sites matter so much. There's a common misunderstanding that we're listening for their TV. Early radio leakage like ours drops as technology matures. Fiber optics and tight beam links don't spill into space. High-power radars and long-haul links leak some, but less over time. If other cultures follow a similar path, leakage is a poor long-range target. Beacons are different, signals built to be found. They cost energy and imply intent. A cautious or efficient civilization may choose not to run one, or to run it rarely, or to aim it at specific targets on specific schedules. That turns the search into a scheduling problem as well as a sensitivity problem. Technosignatures we can try. Short laser bursts. Watch for nanosecond flashes that stick out against starlight. Cheap to send, cheap to see, if you're looking at the right time. Waste heat. Big energy use eventually turns into heat. Wide mid-infrared surveys can flag odd excesses. Early sweeps set broad upper limits. Smaller scale activity could hide below today's thresholds. Unnatural chemistry. Industrial gases at high levels in an exoplanet's atmosphere would be interesting if we can measure them and rule out strange natural sources. That needs repeated, high-signal observations. Artificial lights, in principle. Night-side city lights on a nearby planet could be teased out as a tiny brightness bump as it moves through phases. In practice, that's near the limit of foreseeable instruments. But it's a clear goalpost. Local artifacts, stable gravitational parking spots exist in our solar system. Targeted surveys have checked some. A complete census would need dedicated time and likely space-based sensors. How to look harder in the next decade. Go wider and deeper in radio. Build or repurpose arrays to stare longer at more places with more bandwidth. Sensitivity matters, but so do dwell time, to catch blinks and revisit cadence. All sky monitors. A network of modest, inexpensive dishes with modern digital backends can watch most of the sky continuously and issue alerts when something odd appears. Think smoke detectors for the radio sky. Smarter algorithms, clearer audits. Matched filters are great for pure tones. Complex modulations may need anomaly detectors trained on what the sky usually looks like, but flags must be interpretable. When code cries "weird," observers need to know why. Commensal by default. Any telescope taking time series radio or optical data can run a technosignature sidecar. The more archives we build and share, the more chances for someone else to spot what one pipeline missed. Lightning-fast follow-up. When a candidate pops, minutes matter. A small global network able to pivot quickly reduces "we lost it" stories. This is partly hardware and partly playbook. Who calls whom? With what format? At what threshold? Lunar far-side radio. The far side of the moon is naturally radio quiet. Even a small interferometer there would dodge earthly interference and open low-frequency bands blocked by our ionosphere. Ambitious, yes, but it turns a messy problem into a clean one. Direct imaging pathfinders. Telescopes with coronagraphs or star shades that suppress starlight by factors of billions will let us take spectra of small, temperate planets around nearby stars. That's how you move from maybe to the air contains X, Y, and Z, a path to biosignatures and, eventually, tech-linked gases. If they're there, don't expect a clean jump from nothing to hello. It will come in layers. Sharper nulls, bigger surveys with published limits turn vague quiet into hard constraints. No transmitters stronger than this. In that band toward those stars during these months. Better false alarm handling. We'll keep finding narrow tones, odd flashes, and weird dips that evaporate on second look. Each teaches us new vetoes, new cross-checks, and better follow-up habits. A stubborn anomaly. Eventually, something will survive every veto and come back on command. That's when verification shifts into slow gear. Independent instruments, independent teams, different times of year, and a deliberate hunt for natural explanations. Population questions. One confirmed signal raises a new task. How common is that kind of signal? We'll need surveys tuned to find more of the same and to catch variants we might be missing. So, have we looked hard enough? If hard enough means enough to rule out intelligent life in the galaxy. Not even close. The haystack is enormous, and our coverage is thin in frequency, time, and sky. If hard enough means enough to say something real. Yes, we can already say the nearby sky is not full of loud, always-on radio beacons in classic bands. Bright optical pings are not common among the stars we've watched. Our pipelines, archives, and follow-up networks are improving year by year. What does that mean for the Great Filter? It keeps all three big options on the table. Behind us. If early steps are rare, few peers exist to hear. Silence fits. Ahead of us. If many young civilizations don't stay detectable for long, most will blink in and out between our short looks. Silence fits unless you watch patiently for decades. Quiet by design. If long-lived civilizations use tight beams, encryption, and efficient energy, stray signal to catch unless we're in the line of a deliberate hello. The way to narrow those choices isn't a clever argument. It's better searches, longer dwell times, broader bandwidth, more sky, more revisits, cleaner pipelines, faster follow-ups, and, ultimately, instruments that can read the chemistry of small nearby worlds directly. Until then, today's quiet doesn't mean a lonely universe. It means we've only started to scoop from the ocean. Here's the honest state of play. Modern searches keep turning up interesting signals, and so far everyone checked well enough has turned out to be us, nature, or noise. That might sound like failure. It isn't. Each near miss tightens our methods, upgrades our instruments, and converts a vague silence into hard, testable limits. Progress looks like fewer sloppy false alarms, faster cross-checks, clearer thresholds, and, one day, a signal that survives the gauntlet. Let's tour what search projects actually see, how they verify claims, and what those results really mean. Big dishes, think national observatories, and arrays scan millions to billions of narrow channels around nearby sun-like stars. Known exoplanet hosts, the galactic plane, the galactic center, and even a few nearby galaxies. The classic technosignature is a razor-thin tone that drifts in frequency the way an artificial transmitter would if it was sitting on a rotating, orbiting world. The day-to-day reality is messy. A single observing run can produce thousands of hits features that look narrow, strong, or drift just right. Almost all are radio frequency interference from our own technology. Satellites chatter, aircraft radars sweep, ground stations transmit near the same bands astronomers like. Some signals bounce off high layers of the atmosphere and appear to come from space. Others creep in through the side lobes of the antenna. A few even mimic natural Doppler drift. Good pipelines fight back with a playbook. Shape tests. True narrow lines versus messy splatter from electronics. Drift tests. Does the frequency shift match sky motion or a known satellite track? Multi-beam checks. Real sky signals appear in the on-target beam, not in all beams at once. On-off pointing. Look at the target, then a nearby empty patch, then back. Earth-made signals often follow the telescope. Sky signals follow the sky. Most hits die quickly. The small remainder become candidates, signals worth a second look. That second look is crucial. A candidate must reappear on command when another telescope points at the same star under similar conditions. Best case, 2 or more instruments in different places and run by different teams see the same narrow line from the same sky position while nearby positions stay quiet. That standard kills most claims. A tone that looked perfect at one site turns up when you nudge the telescope, meaning it's local, or resolves into a known satellite when you change the drift model. This is normal science. You don't want the bar any lower. So what do we gain if not a beacon? Upper limits. Teams can say, precisely, in this band, during these hours, toward these targets, there were no narrowband transmitters stronger than X. Sometimes X is framed as if a planetary radar as powerful as ours were operating on a planet around that star, we would have seen it. That rules out one bright piece of low-hanging fruit while leaving fainter, rarer, or differently styled signals on the table. Over time, these limits carve away big swaths of parameter space. The nearby sky is not full of loud, always-on beacons in the most transparent bands. Another bet looks for short laser flashes or ultra-narrow optical lines that stars don't naturally produce. A civilization could ping nearby stars with nanosecond bursts using modest power. A modest telescope could notice them if it's looking at the right moment. Teams have watched hundreds of thousands of star hours. The workflow mirrors radio, flag spikes, reject obvious glitches, demand repeatability. So far, no flash has cleared the bar. That still matters. Bright, frequent laser pings aren't common among the stars we've watched. It doesn't rule out rare schedules, different wavelengths, or targets we've never stared at long enough. Not every technosignature would be a deliberate hello. Some would be side effects of large-scale activity. Waste heat. Big energy use ends as heat. Wide infrared surveys look for objects with unusual mid-infrared excess. Early sweeps suggest galaxy-spanning energy empires, if they exist, are rare nearby. Smaller-scale activity could hide below today's thresholds. Light curve oddities. A decade ago, a star with irregular, deep brightness dips triggered buzz about orbiting structures. Follow-ups pointed to dust and other natural causes. The real win was a playbook. Start with nature. List predictions for each hypothesis. Then check them in order. Unnatural gases. High levels of certain industrial molecules in an exoplanet atmosphere would be intriguing. The hard part is getting spectra with enough signal to be sure, then ruling out odd natural chemistry. That needs repeated, high-quality measurements and careful models. We're at the beginning of that road. Local archaeology. If anyone ever visited, artifacts might park in stable orbital niches, co-orbitals, Lagrange points. Surveys have checked some of these spots. A full census would need dedicated time and likely space-based sensors. So far, nothing obvious. Nature is weirder than we are. Pulsars, the first fast. Regular radio sources were so unexpected, their discoverers half-joked about little green men. They turned out to be spinning neutron stars. More recently, fast radio bursts, millisecond blips from across the universe, were briefly hyped outside the field as potential technosignatures. They're now tied to exotic but natural engines, likely magnetars. The lesson is humility and method. Let the data lead, rule out wild astrophysics before you jump to engineering, and remember that unknown today isn't the same as unnatural. Because headlines sometimes leap ahead of the evidence, it helps to spell out the bar for a true detection. Repeatability. The signal returns under controls, same sky position, compatible drift on different days. Independence. Multiple instruments, preferably at different sites and run by different teams, see it. Localization. Slewing off target makes it vanish. Slewing back makes it return. Nearby positions, stay quiet. Natural vetoes. Known astrophysical processes are ruled out by the signal's bandwidth, polarization, time structure, spectrum, or modulation. Human vetoes, catalogs of satellites, aircraft, ground transmitters, and instrument artifacts are checked and eliminated. Protocol sanity. If there's structure, a modulation. Basic consistency checks pass. If it's a pure tone, its behavior matches what you'd expect from something on a rotating, orbiting platform. Only after that would the community say detection rather than candidate or event. Then the job shifts to characterization. How strong? How often? Any message structure? Other wavelengths? Any neighbors? The search community has learned the hard way that the public pays attention. That's great. It also means being careful with words. Candidate should mean probably interference, but interesting enough to check. Detection should be reserved for the rare case that clears the full bar. Premature claims create a hype hangover that hurts the next real result. By contrast, rapid, transparent data sharing when something odd appears lets many groups try to break the claim. If it breaks, good methods improve. If it doesn't, confidence grows fast. Open archives are a big part of this culture shift. When teams release raw and processed data with enough metadata, others can rerun pipelines, test different drift ranges, or apply anomaly detectors that didn't exist when the data were taken. Several almosts in the past were confirmed as human interference or ruled out thanks to independent rechecks on shared files. It's easy to shrug at null results. Don't. Properly reported, they are the backbone of progress. They rule out loud, always on beacons, in well-studied bands around many nearby stars. They show that bright, frequent optical pings aren't common among the targets we've watched. They set sensitivity floors, thresholds future instruments must beat to expand the search rather than redo it. They improve the playbook. Stronger RFI rejection, smarter scheduling, faster follow-up, clearer public messaging. They populate open archives that tomorrow's algorithms can sift in ways no one anticipated today. Every clean null narrows the gap between we don't know and we would have seen X if it were there. You can read today's scoreboard 3 ways, and all 3 remain consistent with the data. Filter behind us. If early evolutionary steps are genuinely rare, very few peers exist to signal. Silence fits. And the searches become about ruling out the loudest possibilities, while we build tools to find subtler fingerprints of life. Filter ahead of us. If many civilizations pass the early gates but fail during technological adolescence, detectable lifetimes are short. Signals would be rare blips. Patience, long baselines, and all-sky monitors matter more than raw sensitivity. If long-lived civilizations converge on tight beams, encryption, and efficient energy, stray signals are scarce. Detection depends on being in the line of a deliberate hello or on catching byproducts like waste heat or industrial chemistry that physics can't hide. Notice how none of these interpretations are ruled out by present results. That isn't a cop-out, it's a to-do list. Expand the search volume in time, longer dwells. Better revisit cadence, frequency, wider bandwidth with fine resolution, and sky, more targets and all sky watching. While investing in confirmation networks and pushing toward direct imaging and atmospheric spectroscopy of small nearby worlds. Imagine that tomorrow a narrowband signal appears from a nearby star, repeats under controls, and is seen by independent teams. What flips? Instantly, several filters move behind us. Life and intelligence are not unique to Earth. It would not, by itself, tell us how common long-lived civilizations are. A single detection might be like hearing one voice on a dark beach. You still don't know how many people are out there, or how long they've been speaking. The next step would be population work, targeted surveys for similar signals, checks for other technosignatures in the same system, and if we're lucky, content we can decode. Flip it the other way. Suppose that over the next decade we gather strong biosignature evidence, credible life markers in the atmospheres of several nearby rocky worlds, but still no technosignatures. That would nudge the filter forward. Chemistry becomes biology often enough, but technology or longevity stays scarce. Our priority, then, would be reducing the risks in our own adolescence while we keep listening. Look harder sounds vague until you translate it into gear and habits. Longer dwell times and smarter revisit schedules to catch intermittent transmitters. Wider bandwidth with fine resolution, so a single pass covers more of the dial. All sky monitors that run continuously and trigger bigger dishes within minutes when something odd appears. Algorithm diversity. Classic matched filters for pure tones, plus anomaly detectors for complex modulations, with explainable flags so humans know why code cried weird. Cross-wavelength traps. When radio flags something, optical laser monitors and mid-infrared cameras look too open. Standardized archives with rich metadata so new teams can rerun pipelines or try wild ideas without sitting at the original telescope. Pathfinders for direct imaging, coronagraphs, and, eventually, star shades that suppress starlight by factors of billions, so we can read the air of small, temperate planets around nearby stars. Do these things and each no becomes more informative than the last. The haystack stays huge, but our slice through it thickens until a null starts to bite first on the loudest, cheapest to find scenarios. and then on the clever ones. Bottom line, what have searchers actually found? A growing stack of well-behaved nulls, a handful of instructive scares that trained us to be better, and a set of hard limits that future work must beat. That's exactly what you'd expect at this stage. We are early. We are cleaning our lenses. We are mapping out where a signal would have shown up if it existed. The work looks unglamorous until the day it doesn't. And if that day arrives, it will be obvious, because the same habits that produce clean nulls, repeatability, independence, transparency are the habits that make a real detection stick. Next up, we'll slow down and pick apart the most famous false alarms and cautionary tales, from mystery stars and possible biosignatures to suspicious pings, to see what went wrong, what went right, and what those stories teach us about doing this carefully. When someone says, "We found something weird," the internet jumps to aliens in seconds. The real process is slower and more useful. Most weird signals end up teaching us how not to fool ourselves. They harden methods, fix instruments, and set the bar for what would count as real. This chapter walks through famous near misses and what each one added to the playbook. In 1967, radio astronomers noticed a perfectly regular train of pulses. It was so strange, they jokingly labeled the first source LGM1, Little Green Men. The signal became our first pulsar, a rapidly spinning neutron star sweeping a radio beam like a lighthouse. The point isn't to laugh at the nickname, it's to respect the method. The team waited, checked other sites, found more objects with the same behavior, and built a natural model that fit the data better than any artificial one. First impressions mislead. Care beats excitement. A decade later came the wow signal, a single, narrow, strong radio tone in a sky survey. It looked clean and never repeated. That's the problem. One-offs can't clear the bar because they fail the first rule: repeatability. If you can't bring it back on command and pin it to one spot on the sky while nearby spots stay quiet, you don't know what it was. Unknown is allowed in science. Aliens isn't the default. The legacy of that night is simple. A real technosignature has to be refindable and localizable. More recently, a star with irregular, deep brightness dips set rumor mills turning. Some floated orbiting structures as an explanation. Follow-up telescopes watched the star in multiple colors. The dips were stronger in blue light than red, exactly what tiny grains of dust would do. The pattern also changed over time in ways dust could explain. The result wasn't a letdown, it was a template. Start with natural ideas. Write down predictions for each. Gather the right data, and let the best fit win. If something dims a star, color dependence is an immediate check. Dust changes color. Megastructures don't have to. A narrow, drifting radio tone near our closest star once caused a stir. On paper, it looked right. Thin, steady, drifting like a transmitter on a rotating, orbiting world. Then the controls kicked in. Observers slewed the dish on and off the target, changed how they corrected for drift, and called other sites. The tone behaved like local interference. It followed the instrument, not the sky. Other telescopes couldn't bring it back on the star. The case collapsed as it should have. A candidate has to survive on off-pointings, multi-site follow-up, and different drift models. If it acts like gear on the ground, it's ours. A similar lesson came from another nearby star when an odd radio burst lit up the plots. Cross-checks with satellite catalogs and air traffic data pointed to human sources. The science value was operational. It proved why you wire updated catalogs into the pipeline and why you set up automatic alerts so other facilities can try a quick confirmation before the trail goes cold. Optical searches bring their own flavor of almosts. Several programs watch for nanosecond laser flashes or ultra-narrow spectral lines that stars don't produce by themselves. A handful of spikes have looked promising on a first pass, until they refuse to repeat under controls or matched instrument artifacts on reanalysis. That can feel deflating. It shouldn't. Each false start improved the plumbing. Better detectors, cleaner timestamping, stricter coincidence tests, where 2 or more telescopes must see the same blip at the same instant. With lasers, as with radio, once doesn't count. Coincident, independent detections do. Hype also creeps into discussions of possible life in exoplanet atmospheres. When a space telescope reported methane and carbon dioxide in the air of a cool sub-Neptune, some stories rushed to life. Others hinted at a whiff of a molecule linked to biology on Earth. Follow-up work urged restraint. Interesting spectra, not conclusive. Alternate chemistry on that kind of planet could mimic parts of the signal. The right standard for life detection is several independent clues that fit together measured more than once, plus a model that rules out non-biological sources in context. A single molecule rarely settles anything. Closer to home, unidentified aerial reports often get presented as proof of advanced craft. Agencies that reviewed the material have said they see no verified evidence of extraterrestrial technology. Most reports come from sensors not designed for this task, with incomplete metadata and unknown error rates. That doesn't mean every case is explained. It means the data don't meet the bar. In high-stakes science, unknown is not a synonym for unnatural. Instrument, limits, perspective, effects, and missing logs can turn ordinary events into mysteries. Underneath all of these episodes are 3 human traps. First is apophenia. We're good at seeing patterns even where none exist. Second is selection bias. Look in enough places and you'll always find something odd. Unless you adjust for the number of tries, that oddity can fool you. Third is the media echo. A preprint or press release outruns peer review, and the corrections never travel as far as the headline. The antidotes are boring and effective. Pre-register methods when you can. Report nulls. Tally how many shots you took, and use careful language until the checks are done. Put the lessons together, and you can compress the confirmation bar into 1 paragraph. A real signal returns under controls on different days, is seen by independent instruments and teams, localizes cleanly on target. It's there, off target it isn't. Resists natural explanations because its bandwidth, polarization, time structure, spectrum, or modulation don't fit known astrophysics. Clears human vetoes against catalogs of satellites, aircraft, ground transmitters, and site artifacts, and behaves coherently like something on a rotating, orbiting platform or like a deliberate beacon design. Miss any part of that, and you have a candidate, not a detection. If that sounds strict, good, because the same strictness that kills false alarms will make a real detection stick. Near misses don't waste time. They buy reliability. Each one leaves behind better interference filters that stop junk before a human ever looks. Schedules add on, off patterns and quicker revisits to catch intermittent sources. Teams share raw and processed data faster, so outsiders can try to break a claim. Catalogs and site monitors feed directly into pipelines to flag known junk in real time. Communication norms improve too. Papers say candidate instead of detection, and include a follow-up plan in the abstract. That culture, skeptical, transparent, method first, is the culture that will carry the field through the day it matters. What would that day look like? The first hit is unlikely to be a decoded message. It will probably be a repeatable narrow tone, or a repeating optical feature that survives every veto, returns on command, and pins to one star with clean on-off checks. Simple is easiest to spot, so the first signal might be boring by design. A steady beacon or a predictable pulse train meant to be noticed by equipment like ours. Only after confirmation would teams chase complexity modulations, sidebands, or other wavelengths. If the first yes comes from chemistry instead of radio or lasers, say, multiple gases in the air of a nearby rocky world that don't fit non-biological processes, the same rules apply. Repeat it, model it, rule out natural confounders, and gather independent observations with different instruments. False alarms also point to upgrades that are concrete rather than vague. Design observing runs with controls baked in multi-beam checks, on, off pointings, and drift sweeps as defaults. Invest in follow-up speed with a small global network that can swing to a candidate within minutes, so we lost it. Stories fade. Diversify algorithms. Keep the classic matched filters for pure tones, but add anomaly detectors for complex modulations and make every flag explainable so humans can judge it. Coordinate across wavelengths so that when radio sees something odd, optical and infrared look too. Standardize archives with enough metadata that new teams can reproduce or challenge the pipeline without sitting at the original telescope. And train for hype. Decide in advance what words you'll use at each stage candidate. Verification underway. No detection yet, so the message stays sober when excitement spikes. The bottom line is steady. Every famous near-miss pulsars, the single great ping, odd dips, suspicious tones, over-interpreted atmospheres pushes the same lesson. Evidence first, patience always. The public story gets quieter while the science gets stronger. That's the trade you want. When a real signal appears, it will clear the same hurdles that killed the false alarms. And it will do so in public, with independent teams watching. Until then, false alarms aren't failures. They're how you build a detector that won't lie to you on the day it finally matters. The Great Filter is a clear way to frame the silence, but it isn't the only story in town. Over the years, researchers and writers have offered other explanations that try to square so many stars and planets with so little signal. 3 ideas come up again and again: rare Earth, the zoo hypothesis, and the dark forest picture. Each makes a different claim about what the universe is like and why we don't hear anyone. None is proven. All are testable in parts. The point of this chapter isn't to pick a winner. It's to translate what each view predicts, what evidence would move the needle, and what each would mean for us. Start with rare Earth. It says, simple life may be common, but complex technological life could be extremely rare because it depends on a stack of planetary conditions that don't line up very often. Earth's luck may be painfully specific. Long-lived surface water, a climate that stays in the right range for billions of years, plate tectonics that recycle nutrients and act like a thermostat, a magnetic field that shields the atmosphere from stellar wind, a large moon that helps keep our axial tilt stable, and perhaps giant planets parked where they deflect more threats than they send inward. None of those is guaranteed on a random rock. If you need several at once, the odds multiply downward. If rare Earth is right, the universe could be sprinkled with planets that look friendly on a postcard. Rocky, temperate, with hints of water, yet never climb the ladder to animals with big brains and long memories. We might expect to find biosignature hints on a good number of nearby worlds, gases that, together, suggest active biology. We would also expect technosignatures to remain scarce or absent, even as our searches improve. When we finally build telescopes that can read the air of small nearby planets with precision, rare Earth predicts a pattern like early Earth, microbial chemistry, not radio stations. That version of the universe is testable in pieces. We can count small, temperate planets around sun-like stars and then push deeper, asking which ones keep atmospheres, maintain stable climates, and show signs of active carbon cycles. We can look for geophysics by proxy subtle patterns in light that hint at continents and oceans or seasonal changes that look like weather on land. We can listen for planetary magnetic fields through future radio observations that might catch auroral signatures. We can also map how often stars of different types flare and strip atmospheres. If, after a decade or two, we see many living atmospheres but still no technological signatures, not even a nearby repeatable beacon, rare Earth gains weight. It wouldn't be a single smoking gun, it would be the shape of the data. The zoo hypothesis flips the script. It says advanced civilizations exist, but choose not to reveal themselves or interfere with young species like us. Imagine a widely shared prime directive: observe, don't disturb. In a strict version, the galaxy's grown-ups coordinate to keep quiet around developing worlds. Maybe there are watchers parked in the outer solar system, cloaked better than our senses can handle. Maybe there's a policy to contact only after a civilization crosses certain maturity thresholds. Under zoo, silence is not a puzzle. It's policy. Zoo has an obvious strength. It perfectly matches one fact: no confirmed signals. It also has obvious weaknesses. The big one is coordination. Civilizations with different histories and values would have to keep the same plan in the same way for very long times. One loud defector would spoil it. Another weakness is testability. A perfect zoo is designed to be unfalsifiable until we graduate, whatever that means. Still, sloppy versions of zoo leave seams we can probe. Long-lived artifacts parked in stable niches, Earth's co-orbitals, Lagrange points, could, in principle, be found by dedicated surveys. Conditional beacons, devices that wake when they detect certain patterns of activity, might be placed in the neighborhood. If, one day, we found a nearby object with clear artificial design, or a local signal that passes strict checks and behaves like a messenger, zoo would jump from philosophy to evidence. Then there is the dark forest picture, named after a sci-fi metaphor. The cosmos is a dark forest, and everyone moves quietly because any noise could invite danger. In this view, the silence is strategic. It's risky to broadcast when you can't know the intentions or capabilities of listeners who may be centuries away in space and time. With long delays and imperfect information, the safest strategy is to keep leakage low. Encrypt communications, use tight beams, and avoid conspicuous engineering that shines across the sky. The logic is game theoretic. If you can't verify others' goals, and if first strikes are easier than perfect defense, caution wins. The metaphor is powerful, but reality matters. Interstellar offense is hard. Delivering a decisive blow across light years on a useful timeline takes vast energy and accurate targeting against a moving, adapting world. Weapons would arrive decades or centuries after launch. Meanwhile, the target could harden or hide, but the perception of asymmetry can be enough. If even a small chance of attracting a hostile power looks unacceptable, many cultures could choose silence by default. The result would look like a dark forest whether or not actual predators exist. Dark forest and quiet by design can overlap. Even without fear, advanced societies may prefer efficient systems that don't leak much. Fiber-like links inside a system, tight interplanetary beams, heavy encryption, and energy use that ends as modest, well-managed heat. A civilization that values privacy and thrift can look as quiet as one that fears ambush. The difference is motive. The observational prediction few easy signals is similar. A fourth idea sits nearby and deserves a name: non-expansion by preference. Maybe mature civilizations don't care to spread widely. They invest in virtual worlds, art, science, local projects, and long lives at home. They explore with uncrewed probes and slow, careful outposts, not empire-wide bursts. That choice produces little light and radio drama. It doesn't require galaxy-wide treaties, zoo or paranoia, dark forest. It's just a preference. We would notice such societies only if we were very close, or if they deliberately said hello. How do these stories map onto the Great Filter? Rare Earth lines up with filters behind us. Unlikely steps in biology and planet behavior that most worlds never pass. Zoo maps to a filter in culture. Many reach advanced stages, but agree, somehow, to hide. Dark forest maps to a filter in strategy. Many reach advanced stages, but choose silence because risks of shouting look larger than the benefits. Non-expansion by preference maps to a visibility filter. The path doesn't include galaxy-scale conspicuity because most mature species don't seek it. All four can explain today's quiet. The way to tell them apart is not one flashy announcement, but patterns that accumulate. Imagine a few near-term patterns. Suppose we observe several nearby rocky planets and repeatedly see atmospheric mixes that best fit biology. Oxygen paired with gases it shouldn't peacefully coexist with. Yet years of improved technosignature surveys still produce nothing conclusive. That would push us toward Rare Earth or a filter-ahead story. Life is common, technology rare or short-lived. Now, flip it. Suppose we pick up a clear, narrow, drifting radio line that repeats under strict controls from a nearby star, and independent teams confirm it. In a stroke, we move past "we're unique." Rare Earth would need a softer reading, very few, not none. The next job would be population work, finding out how often that kind of signal appears and how long it lasts. There are quieter tests, too. Surveys that set strong upper limits on waste heat in nearby galaxies argue against many energy-hungry empires, pushing us toward Rare Earth, quiet by design, or preference stories. Measurements that show stable climates and tectonic recycling are uncommon on small, temperate planets support Rare Earth. If, instead, Earth-like geophysics look common, scarcity must come later than geology, either in biology or behavior. Searches of our own system's stable orbits that turn up nothing artificial put gentle pressure on sloppy zoo variants. And if decision-makers settle on a cautious policy about active messaging, waiting until our detection and verification systems are stronger, that would reflect dark forest thinking even without believing the scariest versions. Each idea also carries practical advice. If Rare Earth might be true, exploration becomes urgent. Every sample of life beyond Earth rewrites the odds. We should prioritize telescopes that can read the air of small, nearby planets and missions that can test for life in our backyard. If zoo is even partly plausible, we should do local archaeology well. Methodical surveys of co-orbitals and Lagrange points. careful radar and optical sweeps, and a high bar for calling anything artificial. If dark forest pressures are real, we should separate listening, low risk, high value, from beaming, philosophically loaded, hard to undo, and decide in daylight how we want to behave. If non-expansion by preference is common, we should expect that detection requires patience and precision, not louder antennas. It's helpful to separate existence from visibility. Rare Earth is mostly an existence claim. Perhaps there just aren't many peers. Zoo, dark forest, and preference are mostly visibility claims. Perhaps there are many, but their light footprints are small or intentionally hidden. Our tools test visibility first. We can bound beacons, waste heat and atmospheric chemistry long before we can count how many civilizations tried and failed. That means the next decade of work will likely trim the visibility space faster than the existence space. Stronger nulls on big, obvious signals will hurt loud galaxy stories, while slow, careful atmospheric work will tell us whether biology itself is rare or routine. So, where does this leave us? In a better place than the headlines suggest. Competing ideas are not enemies. They are hypotheses with different predictions. As the catalog of temperate, rocky planets grows, as atmospheric spectra improve, as radio and optical archives expand, and as confirmation networks get faster, the room for these stories will narrow. We will either start seeing biosignatures regularly, pushing filters forward, catch a repeatable beacon, moving many filters behind us at once, or keep stacking clean nulls that force us to search smarter or rethink assumptions about behavior. For our choices, the safest plan is to act as if several ideas could be partly true. Build the instruments that can test planetary habitability directly. Keep listening across wide bands with longer dwell times and better follow-up. Conduct local surveys that would reveal sloppy hiding, and treat active messaging as a policy decision, not a hobby, so we don't make irreversible moves based on guesswork. None of this requires fear. It requires patience, clear standards, and a taste for long games. The universe might be rare, polite, cautious, or simply busy doing things that don't splash across our sensors. Any of those paths leaves room for us to last, learn, and eventually take a better measure of our neighborhood. That is the quiet promise. In a quiet sky, the chance to build a civilization that survives long enough to find out which story is true and to be ready whatever the answer is. If the sky went from quiet to something's there, not every discovery would carry the same weight. Some finds would nudge our beliefs. Others would flip major parts of the story at once. The goal here is to spell out, in plain language, which discoveries would matter most, what each would imply for the Great Filter, how we'd verify them without fooling ourselves, and what we'd do next. Start with the simplest, strongest case. A repeatable, narrowband radio tone coming from a specific star, drifting exactly the way a transmitter would if it sat on a rotating, orbiting world. If two independent observatories can reacquire that tone on command, while nearby sky positions stay quiet, we've crossed the line from candidate to detection. Even a bit of structure, a simple on-off pattern, a short header of prime numbers would shout intent. That single fact would shove several early filters behind us. Life and intelligence wouldn't be unique to Earth, but it would not tell us how common such cultures are or how long they last. One lighthouse proves a coastline exists. It doesn't map it. The next move would be relentless verification and careful characterization. Bandwidth, drift rate, polarization, repetition, period. Anything that hints at content. We would not beam a reply on day one. The job is to understand first and share data widely so many teams can help. A deliberate optical or near-infrared laser ping would tell a similar story. Short, bright flashes or ultra-narrow lines that do not match stellar physics, seen independently by more than one telescope on the same target at the same times, would be the optical cousin of a radio beacon. Lasers naturally travel in tight beams, so catching one would also hint at a communication style that is targeted and efficient rather than loud and leaky, that leans toward a quiet-by-design picture. Neighbors who talk, but only down narrow lanes. As with radio, verification would come first. Repeatability under controls, multi-site coincidence, and localization on the sky. Then we would watch at high cadence across colors, check radio and mid-infrared for companions, and look for patterns that say beacon rather than noise. An artifact inside our own solar system would be a different kind of shock. Hardware beats ambiguity, a small probe, a relay, or a dormant monitor parked in a long-term stable orbit, co-orbital with Earth, tucked into a Trojan point, or cruising far out would move, are we alone, from idea to evidence, in a single frame. It would also tilt the interpretation toward restraint. Someone traveled, stayed quiet, and watched. If the object were ancient, we'd learn that at least one civilization survives long stretches of time. If recent, we'd know somebody is active near us now. The response would be slow and careful. Secure the site, record everything, avoid contamination, invite independent teams, and only then decide how to interact. If it transmits, treat it like a beacon and run the full verification playbook. If inert, start with non-destructive inspection and international oversight before any attempt at contact. Another class of clues would come from engineering on a grand scale. Unnatural waste heat mid-infrared glows too bright or oddly distributed to be natural, or transit patterns that match orbiting structures instead of planets would point to conspicuous projects. Multiple systems showing such signatures would undercut the strictest versions of rare Earth. Nobody gets far, and dark forest, everyone hides. It would say, clearly, that some cultures scale energy and build big things without perfectly concealing them. That also implies patience and stability. Giant projects take time. We'd still have to be careful. Dust can mimic heat, and instrument quirks can mimic odd transits. The path forward would be spectra, time series, and independent instruments until natural explanations fall away. Then we'd build a ranked list of targets for next-generation direct imaging telescopes. There is a showy but difficult signal we can imagine. Night-side city lights on a nearby rocky planet. In principle, a direct imaging telescope could watch a planet move through phases and measure a tiny extra brightness when the night hemisphere faces us, consistent with artificial lighting rather than thermal glow or aurora. That would be a mic-drop techno-signature. The bar is high. If we reached it, the follow-through would mirror the megastructure case. Repeat with different instruments and at different times of the planet's year. Rule out natural sources, look for other techno-signatures, and read the atmosphere for chemistry that fits a technological society. A subtler route to the same conclusion would be industrial gases in an exoplanet's air molecules with no easy abiotic path at the detected levels for that planet's conditions. This is a quiet techno-signature. It doesn't require beacons or big engineering, just activity that leaves fingerprints in the sky. The standard here is context and repetition. You'd need strong spectra, taken more than once, and a model that shows why volcanoes or weird photochemistry can't do the trick. If that case holds, it would say not just life, but civilization. And it would lean toward the idea that mature cultures often communicate little beyond what physics leaks. There's also a kind of discovery that would not mention technology at all and still shift the ground. Imagine we detect robust biosignatures, pairs of gases that should not peacefully coexist without biology on several nearby rocky planets. That would be thrilling on its own terms. It would also push the great filter forward. If life starts often once conditions allow, and if we still don't see technosignatures even as our searches grow, the bottleneck is likely later. The jump to technology is rare, or detectable lifetimes are short, or mature cultures are very quiet. The practical reading for us is simple. If the hardest step tends to be in a young technological century, we should behave like a species that wants to extend its lifetime, raise L in the old equation by investing in safety, resilience, A's, and Y's governance. Whatever appears first, beacon, laser, artifact, heat, lights, industrial gases, or biosignatures, the first 72 hours should follow the same playbook. Reobserve fast with the same setup, then schedule revisits over days and weeks. Alert other facilities so independent instruments and teams can try a blind reacquisition, prove localization by slewing off target and back, and by checking nearby sky positions to rule out side lobes and background confusion. Pound on natural explanations with physics in hand. Bandwidth, polarization, time structure, spectra, and modulation are all fingerprints. Pound on human explanations with catalogs of satellites and aircraft, site logs, and electronic signatures. Release data and metadata early so others can try to break the claim. Real detections get stronger under public scrutiny. Weak ones fall apart in the open. And that's a feature, not a bug. For life claims in particular, layer evidence. Observe at different planetary phases. Bring other instruments to bear and quantify abiotic alternatives in the same paper that makes the positive case. It helps to translate all of this into a few if this, then that sentences. If we detect a repeatable technosignature radio or laser, the early filters move backward. The next questions are population and lifetime. How many such emitters exist, and how long do they last? If we detect strong biosignatures on several rocky worlds but no technology, the filter moves forward. Early steps are easy. Late steps are hard or quiet. Our priority becomes extending our own lifetime while we keep listening. If we find a local artifact, both early and late filters move back at once. Someone else passed the gates and stuck around long enough to travel, and zoo-like stories gain credibility. If we see multiple systems with waste heat or megastructure-like transits, conspicuous engineering is real, which weakens both strict rare earth and strict dark forest. And if, after decades of sharper searches, we keep stacking clean nulls while planet counts and atmospheric data explode, the world splits. Either there are very few peers, existence is rare, or many are quiet by preference or policy, visibility is low. Few and quiet can also be true at the same time. People often ask what would be best news or worst news from a filter perspective. Best news, in this narrow sense, would be a long run of sensitive non-detections of life, even as our tools get good. That would suggest early steps are rare, and we might have already passed the hardest gates. It wouldn't prove safety, and it wouldn't justify carelessness, but it would ease the fear that the median young civilization crashes out. Worst news, paradoxically, would be strong, repeated biosignatures on multiple near-Earths. While technosignatures remain stubbornly absent, that would push the bottleneck forward toward the dangerous phase we are living in now. The reasonable response to that case is not panic. It's a boring, serious program to reduce the ways a young technological species can end its own story. If anything real shows up, the world will want meaning on day one. The safest communication plan is to stay inside the method. Use candidate until all checks pass. Explain what was observed, what was ruled out, which tests are scheduled next, and where the raw data can be found. Keep politics and metaphors out of the first briefing. Meaning can wait a week, methods can't. The same habits that have produced clean nulls, repeatability, independence, transparency are the habits that will make a detection trustworthy. The link back to the great filter is straightforward. Signals are not just trivia. They are levers. A beacon, a laser, or a local probe would shove the early filters behind us and make behavior and lifetime the main open questions. Widespread biosignatures with no technology would shove the filter forward and make risk management the main project. Loud engineering would tell us the universe sometimes chooses conspicuity. Years of clean nulls would keep the debate between few and quiet alive while we sharpen our tools. In every case, our homework barely changes. Listen well. Build instruments that can read the air of small nearby worlds. Design verification networks that move in minutes rather than months, and run our own civilization in a way that lengthens its lifetime. Discoveries can move the filter on our mental map. Only our choices move us through the real one. If the great filter is a question about odds, our job is to improve the odds we control. That means doing two things at once. Listen to the cosmos much better than we do today, and build a civilization that lasts long enough to hear whatever is out there. Neither task requires panic, utopia, or grand speeches. Both reward steady, practical work that pays off even if the sky stays quiet. Stronger science, safer technology, sturdier infrastructure, and a culture that tells the truth about what it knows and what it doesn't. Think of this as a plan for the next decade that still makes sense if the silence never breaks. Start by listening longer. Most surveys skim the cosmic haystack in short bursts, then move on. That first sweep is useful, but it misses anything that blinks on rare schedules. We should increase dwell time on each target and bake in revisits on daily, weekly, and monthly cycles. Make second looks the default, not an afterthought. Many almost detections in the past died because follow-up came too late. A calendar that guarantees returns same star, same setup, same time windows costs little and multiplies our chance of catching a real pattern. Then listen wider. The radio dial is huge, and every extra octave covered at fine resolution turns one night of data into 10. The same idea applies across the sky. Keep targeted programs for promising stars, but run continuous all-sky monitors in the background. The targeted work finds what we expect. The monitors catch the unexpected. A sweep, a burst, a slow drift where nobody thought to look. When either stream flags something odd, the other pivots to help. This is not complicated. It's just discipline about bandwidth, coverage, and handoffs. Speed matters as much as sensitivity. A candidate that waits days for confirmation often becomes a ghost story. Build a small, global follow-up network with a shared playbook so multiple sites can pivot within minutes. The hardware is modest, some dish time, fast backends, time sync, but the rules must be crisp. What counts as a drop everything alert? Which numbers go in the message coordinates? Bandwidth, drift, confidence. Who logs what? How to show on target it's there, off target it isn't. If the answer is a satellite, we learn it fast and move on. If it isn't, we don't lose the moment. Smarter eyes will cut the noise. Classic matched filters are great for razor-thin tones, but clever signals may look like structured noise unless we train models on the normal sky and ask them to flag departures. That doesn't mean trusting a black box. Every alert should be explainable. Show the features that triggered it, the drift the code inferred, the beams that saw it, and the beams that didn't. The goal is to spend fewer human hours on junk and more on the handful that survive first contact with the pipeline. Open data is a force multiplier. Release raw and processed files with enough metadata for others to reproduce the search. When peers can rerun your pipeline or try a different drift range or anomaly detector, two things happen. Real signals get stronger under many eyes, and bad candidates die quickly without becoming myths. This also improves craft. People write clearer code and pick defensible thresholds when they know others will read both. Transparent by default is a habit that makes future confirmations faster and safer. Better listening won't matter if we don't last. The same century that gives us sensitive ears also hands us tools that can harm us at scale. The right answer isn't fear, it's guardrails that let progress continue without turning one mistake into an ending. In AI, that means independent evaluation before deployment, red team testing by groups who don't report to the builder, containment that actually turns systems off, and audit trails that make responsibility real. Add simple but vital coordination. Incident hotlines so weird behavior doesn't spark panic. And common reporting formats so one lab's lesson spreads before the next lab repeats the error. Capability tends to spread faster than safety unless we choose the opposite. Biology needs the same mindset. Most biotools are dual use. The same methods that cure can harm if misapplied. Practical steps are boring and essential. Higher lab safety standards, real audits, better ventilation and waste handling, and privacy-preserving pathogen surveillance that spots unusual patterns early. Keep rapid vaccine and treatment platforms warm in peacetime so they're ready under pressure. Put the riskiest work under strict, clear rules with carrots for compliance and real penalties when safety slips. While preserving safe paths for helpful research, we don't need to slow discovery. We need to stop preventable accidents and make intentional misuse harder. Nuclear risk is the old problem that stays solved only if you keep solving it. The checklist is familiar and still right. Maintain early warning systems to reduce false alarms. Keep communication lines open even between rivals. Reduce hair trigger postures where possible, and rehearse crisis scenarios together. So, the first tense call isn't the first call ever. Drills sound naive until the night you need them. In every field with high stakes and short timelines, aviation, emergency medicine, spaceflight practice beats bravado. Resilience is the unglamorous part. Modern life runs on tightly coupled networks. Grids, satellites, cables, logistics, data centers. Tight coupling boosts efficiency and fragility at once. The fixes are plain. Add buffers and spares. Stock critical components. Segment networks so a local failure doesn't cascade. Keep manual fallbacks for machines that control physical systems, and plan for space weather with rehearsals that last longer than a press release. Efficiency is a good goal. So is slack. A durable civilization buys a little of both and regrets neither. Planetary defense is simple. Keep looking for near-Earth objects, test deflection methods in peacetime, and rehearse decision chains so money and hardware move the day a clock starts. The price is tiny next to the damage of being unprepared. More important, the habit it builds applies everywhere. Define trigger points, assign roles, and practice across agencies until people can do the right thing under stress without a meeting. Truth is infrastructure too. When warnings arrive about a candidate signal, a software exploit, a lab incident, people need places to see the same facts. That means supporting institutions that can investigate accidents and near misses without making every report a political weapon, protecting rigorous science and responsible journalism, and copying practices from fields that already beat down error with procedure. Aviation learned to share black box data without blame, so the same crash never happened twice. Clinical medicine learned to run trials and publish negative results. Software learned to use reproducible builds and code review. Those aren't slogans. They're checklists we can steal. Exploration belongs on the list because it changes the meaning of the silence. Close to home, that means missions that can actually look for life and say yes or no with a straight face. Better drills on Mars, careful chemistry in the oceans under ice, sample handling that avoids contamination and overclaiming. Farther out, it means telescopes that can read the air of small, temperate planets around nearby stars and observe them more than once. So we trust the answer. If early steps are common, we'll see it. If they're rare, we'll see that too. Either way, we'll argue less and learn more. Active messaging deserves daylight, not dares. Announcing ourselves on purpose is a choice with long timelines and uncertain payoffs. Treat it like other high-stakes choices. Set goals, list risks, define triggers, create a process the public can see, and leave room to change course as evidence comes in. A simple near-term policy is a pause on one-off hello stunts, while we keep listening hard and build the science and diplomacy to decide together. Listening is cheap and reversible. Broadcasting isn't. You might ask what all this costs. The answer is less than the bill for not doing it. A serious listening program, wideband arrays, a nimble follow-up network, open archives costs less than a big stadium and pays off for decades across astronomy, signal processing, and education, strong lab ventilation, stockpiled medical supplies, and grid buffers look expensive until the day they save money in hours. The math shows up after every storm, outage, or recall. Redundancy is a waste right up until it isn't, and then it's priceless. Notice the design principle here. Pick actions that help in many futures. Better telescopes help whether the galaxy is busy or empty. Safer AI, safer labs, sturdier grids, and honest institutions help whether we are alone or not. Planetary defense helps whether the next century brings visitors or just meteoroids. That is how you hedge against an unknown filter. Invest in moves that are wins across scenarios, not bets that only pay if one story is true. There is also a quiet reason to do this that doesn't fit on a slide. We don't only want to survive long enough to hear someone else. We want to be worth talking to when that day comes. The traits that raise our odds, patience, restraint, curiosity, accountability, are the same traits that would make first contact. If it ever happens, something more than a loud hello. You don't need to believe in watchers, treaties, or cosmic dangers to believe that becoming steadier and kinder is a good use of a century. So we listen longer and wider. We set up fast follow-ups and share what we find. We harden the parts of our world that break too easily. We keep powerful tools on short leashes until we know they won't run. We plan for weird nights so weird nights do less harm. We explore nearby worlds and read far-off skies. We treat speaking for Earth as a decision, not a dare. None of that will move the stars. It will move us. And that is the point. A quiet sky is a puzzle we can't solve alone. But a longer-lived, clearer-headed civilization is a key we can forge ourselves.